So next, I have the lovely pleasure to introducing Ebony Smith, who's going to talk about her research at what's called an ignition point sensitivity study of the WRF-Fire model and analysis wildfire area and location. A fun fact about Ebony is that, like, while she's generally horrible at being funny on command, when she's not on command, she does have pretty funny moments.
Thanks for that, Malcolm. It's right. He's true. I really am not really good at joking on command, but fun facts for me, typically I'll be like, okay, well, my favorite color is purple, and that's it. That's besides the point. So this summer, I did a research project on the WRF-Fire model. I did a sensitivity study on how the change of ignition point location could change the output of wildfire area simulated by the model as well as location. And I had the pleasure of working with my mentors, Amy DeCastro, Amanda Symes-Anderson, and Clara Chu, who have been immensely helpful in my progression this summer, as well as the SOARS staff, Lorena, Khadija, Jeff, Laura, as well as the SOARS cohort. I'm so happy and so proud to be a part of this cohort and very appreciative of it. So I want to start my presentation by asking everyone what you guys think about the number one cause of wildfires is. Okay. All right. So, yes, the answer is people. The number one answer is, according to the National Park Service, the number one cause of wildfires is by humans, which is kind of sad, which is why there's a growing concern for the increase in population in Colorado and the wildland-urban interface. And the wildland-urban interface is simply a term used to explain an area where wildland fuels and human developments and structures interact. So as you can see, right in the middle here, there's a lot of purple and dark blue, which just indicates there's a lot of people and wildland fuels intermingling together in that area. And it's also important to note that the WUI, what we call the wildland-urban interface, it has doubled since the year 2000. So with the WUI doubling since the year 2000, it also has a growing concern and maybe a correlation between the average annual amount of acreage burned by wildfires each year in Colorado. As you can see, there has been a tenfold increase since the 1960s. And because of this increase in average annual acreage burned by wildfires, which may not just be because of humans, but it could also have to do with the climate change going on here in Colorado. And what I mean by that is there has been increased temperature, average temperatures, as well as lengthened wildland seasons due to drought. So because of this, Colorado has funded a bill to support the development and advancement of the COFIBS project, which is just the Colorado Fire Prediction System, which is used to integrate the WRF-Fire model into a decision support framework for end users. So what the model does is it takes input data such as ignition point location, fuels, terrain, and weather to get some output such as the progression of the propagation of the fire, as well as areas burned, as well as different things like heat and flux. And then, so that's, for me specifically, I'm looking at the fire area burned as well as the location of the fire area burned so that we can better support the end users and let them know how to best mitigate the fire. So the case study I'm working on has a total of 10 different case studies. However, I'm focusing on the Indian Valley Wildfire, which took place in 2018. So this is an image of the wildfire burned within the first 6 hours of the ignition time. And the green dot is the ignition point, and the gray area is the area burned. Can anyone tell me something odd about this image? Malcolm.
The ignition point is not within the burned area.
That is correct. The ignition point is not in the burned area, which is not normal. The ignition point is where the wildfire starts to spread from. And the reason for this is because firefighters, when they respond to a wildfire, they hear about it and they fly above and they plot their best guess at where the ignition point is. And it's not always accurate in time or spatially. So what we're trying to do is learn how change of ignition point influences output from the model. So some things that we took from the Indian Valley Wildfire data is just some things like it was northwest of Colorado, so it was in a rural area, it did not harm any civilization. It started July 20th of 2018, and it's important to note that it did not end anytime soon. It still was going until August 2nd, 2018. And then it burned a total of 6,310 acres, and it was in a pretty relatively dry area. So looking at my sensitivity analysis, what I did is I inputted a total of 17 ignition points into the model. First, we used OG, which is just the reported ignition point, simulated into the model. And then we spread out 100 meters, and we calculated 100 meters out north, south, east, west, as well as northwest, northeast, southeast, and southwest. And then we did that again for 200 meters out. As you can see by the orange dots are 100 meters out, and the dark red dots are 200 meters out. And so what we did is we then looked at the area results. We started with that and then went on to location. So from the area results, we found that the largest area burned was burned by N2. N2 was just the ignition point 200 meters above the reported ignition points. And then the smallest area burned was simulated by S2, which is 200 meters south of the reported ignition point. And it's important to note that the variance between the two is over 2 square kilometers, whereas when I looked into the difference for ignition points 100 meters out, though they did not produce the largest nor the smallest areas burned, they did have a variance of no more than 1. It was actually 0.7. So there's a big variance between 0.7 and 2.2. So then I looked at results. And we started by looking at results by looking at the area burned. And then we placed an envelope around it to learn the northernmost, southernmost, easternmost, and westernmost extents of the wildfire, so that we can learn how they shift in location. And what I mean by that is that we would compare them to different types of envelopes from different wildfires. For instance, you see that the northernmost extent for N2 is much more north than that of West 2, and West 2 has a much western extent than N2. So to look at it more condensedly, we plotted it on a y-axis of latitude here and a x-axis of the cardinal direction that it was moved. And so as you can see here, it's important to note that in the 200-meter range, we see the northernmost extent towards the top here and the southernmost extent at the bottom here for both plots. And the northern plot, the northernmost extent was simulated by North 2, and the southernmost extent was simulated by S2. And then for the 100-meter plot, Southwest simulated the most northernmost plot, and Northwest simulated the northernmost extent, and Southwest simulated the southernmost extent. But it's important to note the variability here. You see that the variability here and here is much different. It's larger here than it is for the 100-meter range, and then it's also, again, larger here for the longitude. So again, we have on the y-axis, instead of latitude, we have longitude, and then we have the cardinal direction moved on the x-axis. There's a lot of consistency here, much more consistency than we saw with the northern and southern extents, and a lot more variability here when we broaden out to 200 meters out. Again, we want to look at the points that simulated the most eastern and western extent. So we see here that northeast 100 simulated the most eastern extent, and then northwest, I can't see from here. Northwest simulated similar to the rest of the most western extent. And for here, we see North 2 and Northeast 2 both simulated a further east extent, and West 2 simulated a very western extent. So that led us to look at the overall performance of the simulated ignition points. So here we look at the probability of detection on the y-axis and the success ratio on the x-axis. What the probability of detection is simply the amount of overlap or intersection between the observed area and the simulated area burned. So as you can see here, this gray area is the observed area, and then the forecasted area or the simulated area burned is this red area, and the purple is the intersection. So as the intersection increases, we get a closer value to 1, which is good. And then as these red areas increase, we get a lower success ratio because this is based on the false alarm. So this is the missed areas. So as you can see, the blue dots, which represent the range for distances 100 meters away, we see that they are very closely clustered together. Whereas when we look at the ignition points that were 200 meters away, the range of variability increases once again. I want to point out that the perfect performance would be up here, just so you guys know. So that led me to look at the deviation from the average, just because that's kind of what I'm interested in. So I was looking at how south, west, and south both performed below average for the probability of detection and the success ratio, whereas north, northwest, and northeast both performed well above average. And then as you look at the ranges for the distances 100 meters out and 200 meters out, again, because you see the 100 meters out is in a lighter red than the 200 meters out, you see that the range of variability, once again, is much larger between S2 and North 2 because I don't know why, but we're looking into why. So that led me, and so in summary, we found that model variability increases as distance from the reported ignition point increases, and this result occurred for location, especially between northern and southern extents, rather than eastern and western extents, and that this also occurred between probability of detection, success ratio, and as well as the area simulated. So some future work that I'm hoping to do in this next week is just to look at how I want to look at a specific case or a specific ignition point that simulated an area, and I want to learn why it simulated it like that. So I'm looking at different things like weather conditions such as wind, terrain elevation, as well as fuel conditions. The point of interest that I'm looking at is East 2, because East 2 is the only 200-meter cardinal direction that did not simulate the furthest east condition. What I mean by that is that when you look at N2, South 2, or West 2, they both simulated either furthest north, furthest west, or furthest south, respectively. So East 2, despite what I would have concluded or thought, it simulated an ignition point it simulated an area that was further west than NE2 and N2. So I want to look at these ignition point areas and where they burned to see why it did this. In addition to that, I want to look at other case studies with distorted ignition points. So just looking at ignition points outside of the fire perimeter again with similar fuel characteristics. And then also looking at other contrived ignition points. What I mean by that is just furthering the distance between the reported ignition point and the simulated ignition point. So looking at it from 300 meters out, 400 meters out, and seeing if the range of variability continues to grow. That is all I have for you guys today. Thank you so much.
Question.
Pedro.
Great presentation, Ebony. Is this something you're considering doing for grad school?
No, I'm not. I really want to look into the coastal areas. I'm from Virginia, so I'm used to having a little bit more rain, less wildfires.
Ebony, great presentation.
Could you go a couple slides back? Keep going.
Tell me when to stop.
Yeah, I'll tell you. Oh, there. Yeah.
Okay.
Next one.
Longitude or latitude?
The next one. No, actually.
Okay. Got no.
No. It was the line one. It's the line one. Yeah.
The performance diagram.
Yeah, the performance diagram. Perfect.
This one.
Yes, I was wondering, could you explain a little bit more what we're seeing with the lines and all that?
Okay. Well, we are looking at the, one second. The dash line, and I don't know. No. Okay, so I'm going to try my best to explain this to you guys. So we are looking at the critical success index and the bias. And I'm pretty sure the critical success index are these dashed lines, and the curved lines are the bias. I could have them flipped, but we're looking at those two variables there.
Like the dots just indicate like where.
Oh, the dots. Oh, you want these?
No, yeah, and they just indicate like how that performance was.
Yes, so we're looking at the probability of detection. So we're looking at how well it forecasted. So if the observed area, how much the observed area and the simulated area intersect, rather than, and then the success ratio is looking at how much it doesn't. So how much the forecast simulated an area, but it missed it. So it's saying that the observed area did not actually burn in that area. Did that make sense?
Yeah.
Okay.
Any other questions? Okay,
Thank you.